guys, in this video we're going to talk about the subject of inductance or self-induced EMF. So the scene opens, we've got a very simple circuit here with a switch, a battery, and a resistor in it. And the question that we're going to ask here is, what happens to the current when you close the switch, right? And so most people's answer here is this really even a question? Like, I close the switch and current starts to flow, like, you know, the lights turn on if this is a light bulb. So of course, this is what happens with the current, right? You go from nothing when the switch is open to, at the moment the switch is closed, suddenly this amount of current, right? EMF over R. All right, the reality is that's not actually what happens. And we can explain this knowing what we know about Lenz's law. Here's what actually occurs. When you close that switch, assuming it's a normal circuit, you don't have any funky extra components called inductors that we're going to learn about, the current increases incredibly fast, but not instantaneously, to whatever this value is, EMF over R, okay? So it's not instantaneous, right? It's not zero and then nothing, because frankly, nothing is actually instantaneous in physics. Everything takes a certain amount of time, right? So the current doesn't immediately go from zero to the maximum. There's a sort of ramping up to whatever that maximum value is. If I zoom in on this curve, you're going to see a very familiar shape. It's going to be the natural growth curve. Oh, that's interesting. All right, now, why on earth does this happen? Why isn't it instantaneous? The answer comes back to Lenz's law and Faraday's law of electromagnetic induction. All right, so looks like this, in case you need the reminder, right? The EMF induced in a loop is equal to the negative rate of change in the flux through the loop. When the switch is open, there is, of course, no magnetic field inside of this loop. Then you went and you closed the switch, all right? When you close the switch, current does begin to flow. Using the second right-hand rule, you could say now that there will be a magnetic field inside of the loop which points into the page. Thus I've drawn all these X's. We went from having no magnetic field to some magnetic field inside of a loop that has a certain amount of area. Therefore, there's a rate of change in the flux through the loop, and the system, according to Lenz's law, is therefore going to react to this change in such a way as to try to produce a current which is going to oppose the change in flux. All right, so we went from having no field to having X's. Therefore, the induced EMF is going to try to make a current which goes in such a way as to make dots. In other words, it's going to be this way. And so, even though this is the only battery in the circuit, your induced EMF is acting like a second battery, which points in the exact opposite direction. All right, so in other words, the system is actually trying to oppose the current that the battery is producing, right? Always the goal is for the system to try to oppose the change in flux. Therefore, we get an induced EMF which opposes the battery. Mr. Errico, how is it possible that you ever get current then? Because, I mean, if you've got one EMF this way and another one that, they're not equal. They never are. Ultimately, the battery always wins, which is what you see from this graph, right? The change is not instantaneous due to the induced EMF, which we get from Lenz's law. However, the battery does ultimately win the day, and we get current flowing like normal through the circuit. Okay, now that's under normal circumstances. Physicists being physicists and electrical engineers being who they are, this phenomenon is, of course, exploited deliberately in the form of an electrical device called an inductor. Sorry. In this next part of the video, we're going to talk about that's spelled wrong. It's not pronounced the inductinator. It's just the inductor. Inductor, all right? An inductor is this thing that I was lifting, which you may recall is actually also called a solenoid. Yeah, this is a solenoid, right? Its purpose is, when we call it a solenoid, to make a magnetic field. However, it also functions as an inductor, right? The reason it works as an inductor is because it has a large magnetic field that can build up inside of it. Therefore, if you have it hooked up to a battery and then you try to make current pass through it suddenly out of nowhere, there's going to be a massive change in the magnetic flux through this inductor because it makes a big magnetic field and has a cross-sectional area. All right, so given, therefore, that you've got a sudden change in the flux through the loop here, this functions as an inductor where it's going to oppose the change in flux, the increase, by inducing an EMF which produces a current which would make a field which goes in the opposite direction to oppose the change in flux. Okay, all right. All that's a lot of words, all right? The big idea is pretty much inductors look like a coil of wire. So a solenoid is an inductor. And therefore, if you see it in a circuit diagram, it's that. That right there is an inductor. For some reason, the symbol for an inductor in a circuit diagram is an L. I have no idea. That's just what it is. Kind of like with other circuits or other circuit components, you've got like V equals IR, tells you the volts used by a resistor, and V equals Q over C tells you the volts used by like a capacitor. This has an equation as well for how many volts it uses. All right, what is that equation? Here is that equation. The volts used or produced by your inductor are given by that equation there. L, that is the inductance, as it is called. Inductance is measured in, of all units, the Henry, which is, of course, a capital H. You thought I was going to say some other letter, didn't you? Like a Greek letter. No, it's just an H. It's a regular old H. The d/dt part of it there is the rate of change in the current. Meaning specifically the rate of change in current through the inductor itself, right? So the inductor doesn't care about what's happening in other parts of the circuit. It's just going to produce a voltage if you do something like try to change the current that's going through the inductor. All right, now, like with most things in electromagnetism, it's worth noting that it's not so much the values themselves that matter as it is the rate of change in those values. When we did Faraday's law, right, of electromagnetic induction, right, Faraday said the induced EMF is proportional to the rate of change in the flux through a loop. It didn't matter what value the flux was. All that mattered was the rate at which it was changing, all right? Same thing goes here for the inductor, right? If there's a current passing through it, whether it's 1 amp, 0.1 amps, or a million amps, the amount of current, whether it was any of those various numbers, was irrelevant as far as this equation goes, right? All this equation cares about is the rate at which the current is changing. So if you go from there being no current to there being some amount of current, or you go from there being some current to there being no current, in both of those cases, there's a change, therefore there's a rate of change, and therefore the inductor is going to oppose the change by producing a voltage of its own. Okay, so this therefore is going to lead us into the topic of RL circuits. Okay, so but in basic terms, right, this is your inductor, it's a coil of wire, and you're going to see this equation a lot for the volts that are produced by that inductor. All right, next up, the RL circuit. So the RL circuit is, as you may have guessed already from the name, a circuit that contains resistors and inductors. This is as opposed to RC circuits, which contain resistors and capacitors. And I'm actually going to bring up RC circuits again in a little bit, not just to say, oh, and here's another one on the list. There are important contrasts to be made between the behavior of RL circuits and RC circuits. In fact, in a lot of ways, they act in completely opposite fashions. All right. Okay, so the RL circuit. We've got an EMF, we've got a resistance, we've got an inductor, and then this switch can move between, say, this position and that position. We're going to start off by putting it right here into the, I guess we'll call it position A, right? Connected up to the EMF. All right, now the important thing to remember about the inductor is it doesn't want the current to change. So before we close the switch, the amount of current through the inductor is 0. And the inductor is perfectly happy with whatever is happening right now. Okay, so whatever's going on now is what it wants to happen, right? If there's any changes, that's where the inductor gets angry and tries to make an EMF. So at the very moment that you close the switch, the current in the circuit will remain 0 because the inductor said so. Or at least the current through the inductor will remain 0. Okay, it literally can't stay that way. All right, ultimately the battery is going to win and there will be a current, but at the very moment that we close the switch, we don't go from no current to some current. We go from none to still none for an instant. Okay? So if I made a graph of current as a function of time, it would look like this. All right? So the important idea here then is that initially the inductor prevents any current from flowing at all. It will not let anything pass through it. All right, a long time later, the rate of change in the current is in fact 0, right? Once you reach that steady state current, the inductor doesn't do anything because the rate of change in the current is 0, right? This line is flat near the end, or nearly flat, right? And so therefore there's no rate of change. The inductor doesn't produce any volts to oppose the battery, and so we max out at EMF over R because the inductor is doing nothing whatsoever. All right, if we then move the switch from position A to position B, the inductor will be like, whoa, hold on, where'd the battery go? I need there to be current. There was current a second ago, and so the inductor's whole goal is to keep the current constant. It does not like change. It wants it to stay the same. And so instead of getting an instantaneous drop-off when you move the switch to B, what will happen is you get an exponential decay. So there is a period in time where the inductor is able to maintain the current, right? It acts like a battery. It says there shall be current in the same direction that it was already flowing, and it will maintain that for as long as possible. All right, now in case you're wondering how that works in terms of energy or anything, there is an equation I'm going to put up right now, which is the energy stored in an inductor. I'm putting that up there right now because I always forget to include it. And so there, it's now included in the lesson. All right? All right, so in other words, there is energy stored in the magnetic field which exists inside of the inductor. So even if you unplug the battery, that energy stored in the inductor is going to be sufficient to cause there to be current for some amount of time longer. And we'll learn how to write equations for that. But this is the graphs that you would observe for moving the switch to A and then moving the switch to B. All right. Next up, we're going to do some actual math with this instead of just presenting graphs.